In this video, we're going to talk about top-down design using functions. Um, last video, in the last lecture, we talked about one benefit of using function. The main benefit was code reuse. And arguably, a top-down design is as important as the code reuse. So especially this top-down design issue becomes more and more important as the size of the program gets larger. So as an analogy, let's think about this situation. You start a business. So you want to run your business. What would be the essential step? You're going to hire employees, right? And one of the most essential steps is dividing your work task between employees. So you have to give a clear-cut job description and duty assignment for each employee, right? And that ensures that all necessary tasks are completed. And assigning specific duties also allows employees to specialize and perform their task efficiently. So if you don't actually, divide this work task in the right manner, then you're not basically using the labor from the employees in the right manner, and then it's likely that you cannot succeed in your business. Especially when the size of the business grows really large, then assigning job is not really enough. You have to think about like good hierarchical structure so that like all these functions work really well and interacting with other functions. Something like this happens when your code gets larger. So you got to manage your code. What does that mean? That's the top-down design. So you cannot write 1 million lines of code in one function main. If you do that, what if there's a bug? It's really hard where the bug is because you have to scroll down all the billion lines of code. That's impossible. So that means what? You have to divide the program's entire task into smaller jobs. In the computer science terms, we're usually call that as reducing the program task into smaller tasks. So this notion of reduction will appear in the advanced course more and more often, especially in the theory of computation algorithms. So this notion of reduction is always everywhere. Anyway, so you gotta divide the big task into smaller tasks, and then small task into more smaller tasks, something like that. So for each small job, in C programming language context, for each small job, you have to make a good function. Okay, you got to give a good name for the function. Okay, name is important. Okay, if you can give a good name for the function, that usually means you split the job well. You split the entire program's tasks really well, and then somehow probably the detail of writing your function comes out naturally too. If you don't like the function name, you may want to think about again, am I splitting the job right manner? And then for hierarchical structure, sometimes the one function still does too many things, it's too big. The job size is too big. For that case, you may think about splitting the job into smaller functions, something like that. So the way to do this gets important, especially for your second project. So the size of the project gets bigger. Your program will get bigger. And then it's almost impossible to write one main function and be done with it. It's impossible. You will see it. So the right way is what? We'll split the job into roles. And then, for each role, for each function, for each task, you have to write a good function. Give a good function name and think about what will be the input and output of the function. Yeah, that's the design, and that's what we are expecting you to be able to do so. especially in this entire Sears career. So this is the excerpt that I copied from Wiki. So when you do the practicum, when you do the capstone at the end of the semester, at the end of this major, the last semester, what do you have to do? You gotta, create really like big size program. So it's, in a sense, it's a programming large, right? So with the programming in large, somehow you have to manage the code. Well, you may co-manage it, but anyway, coding managers place emphasis on partitioning work into modules with precisely specified interactions. This requires careful planning and careful documentation. Something like this should be done, although in this case only by yourself, but something like this, you should be able to, some skills like this, you should be able to acquire. Programming in large requires abstraction, creating skills. Until a module becomes implemented, it remains an abstraction. That means what? You're thinking about generally in an abstract manner, okay? I gotta do this, okay? I'll feed input, I'll get the output. But I won't think about the detail now, okay? I'm gonna use it. Taken together, the abstractions still create an architecture unlikely need to change. If you have that kind of abstraction, make this abstraction really well, then probably you can write the main function without writing the definition at all. Right? So they should define interactions that have precision and demonstrable correctness. So programming in large requires management skills, the process of building abstractions, if not just to describe something that can work, but also to guide the direction, direct the efforts of people who will make it work. Okay, so if you do this top-down design really well, then actually that already have some guidance, especially in the name of the function and also like the input and output specification of the function. So when you do homeworks and labs and projects from now on, you really think about this abstraction, top-down design. Okay, that's really critical skill to be a good programmer. As an example, let's think about this. So you have a bank account whose annual interest rate depends on the amount of money you have in your account at the beginning of each year. Okay, rate. Your annual rate starts at 3%. The rate additionally grows by 0.5% for each 1,000 in your account. The rate cannot exceed 8% max. 8% is the max. And for example, if you have that amount, that's basically 3 plus 3 times 0.5, which is 4.5%. And compound. Interest in this account is compounded monthly at annual rate. Okay, that means what? You're given an annual rate, and then divide by 12 is the monthly rate. And each month, for each month, the interest is compounded. Transaction. Each year, you also make a single transaction. It's going to be deposit or it's going to be withdrawal. So every year you can do only one transaction, either deposit or withdrawal, before the bank figures out what your rate is. Okay, and you're given this specification, and then what? You are expected to write a program that simulates 5 years under this system, interactively querying the user for transaction at the beginning of each year, as I said, and returning the balance at the end of the 5th year. Okay, how do you do that? Well, you have to think about the top-down design. What is the important things? How do you split this job? In a sense, it's obvious because I gave you the bullet points, right? So you have to have some function to compute the rate, first bullet. And then you have to think about how to compute the compound interest. Given the annual rate, okay, you have to divide by 12, and then what? You have to compound every year, every month. This means 12 months. So you got to compound by 12 times. And transaction is basically deposit or withdrawal. So that means you have to prompt to the terminal, again, and get the input from the terminal, whether it's deposit or not, and then the amount. And then based on that, you do transaction. So modify the balance. Okay? So at least you got good function names: rate, compound, and transaction. Okay, what would be the input? Let's first think about the rate. What would be the input? Well, rate depends only on the balance, right? So if the balance is 3,000 something, you know the rate. So that means the input of the rate function is double balance. And then output will be the actual rate. Okay. What about the compound? Compound is what? Given the annual rate, okay, you actually find out the actual interest rate, right? That means what? Again, you get the rate, and then you actually return the rate. Compound rate, monthly compounds. So function would give you the value of $1 after year's monthly compounding with annual interest R. And if your balance is B, your rate R is the beginning of the year, your new balance will be basically B times the compound rate, which is the output of the compound function. Okay. And then third one is what? Well, you have to give the original balance, and then transaction will take care of the inputs from the terminal and then modify the balance, and that should be the output. Okay, now you identify the really important useful functions, and then what do? Well, you have to use it in the main function. So the main function becomes now is super easy, right? Initially the balance is 0, and then because you are simulating 5 years, you have to use for loops 5 times. What do? First, in the beginning of the year, you do transaction, withdrawal or deposit. And then now balance is changed. And then what? Based on the balance, you compute the rate. Remember, you can actually use the function inside the function. If that's the case, rate is computed first, right? And then rate is what? Modified rate based on the balance, right? And then you actually compute the compound rate and then multiply with the original rate. And that's basically interest included. And then that's the simulation for 1 year. And then you do that 5 years, and then you print out the balance at the end of that. That's main. Super easy. So, we don't need to worry about for now when you write the main function. You just think about what is the right prototypes, and think about good names for the functions, and then use the function, abstract out, and then work out the details after writing the main function. So that's the main gist of the top-down design. Okay. So if you want to look at the actual code, okay, so that's in the course homepage. Remember, so you include standard.h and then give the right prototype. And the main function is basically what we saw before. And then how do you implement a transaction? Transaction is what? Well, you have to print out, okay, ask, is it withdrawal or deposit? If it is withdrawal, write W. If it is deposit, write D. And get that into character variable act. Okay, you have to also get the amount. So get the amount. And if it is W, withdraw. If it is what? Deposit, you add. And then return the modify the balance. That's the transaction. It's easy. You don't need to worry about anything else. You don't need to about the big picture or anything. Just when you write the transaction, you just need to, well, given the original balance, you think about given the original balance and then what would be the modified balance. What about rate? Well, starting with 3%, right? If you have 1,000 more, you gotta add 0.5, and this is integer division, so it's really the quotient. That's how you do it, and max rate is 8, so this is it. And you just return the rate. And then compound rate is what? Because rate is percent, so actual real number is computed by divided by 100. So that's scale rate. And then what? How do you get monthly interest rate? Divided by 12, right? And then you compound it for how many times? 12 times. And you return the compound rate. And you're done. Okay? So it's really important to get this idea or skill of top-down design. So that will be critical, especially for your project.